Brilliant. Thank you very much. So first of all, I would like to thank the organizers for organizing such a great conference, and I hope that we can all meet in person soon in Marseille. So this is work on integer-valued time series, and this is joint work with Mikkel, Bennedsen, and Asger Lunde from Aarhus, and with Shephard from Harvard. And this is still work in progress. So I'm just going to present you what we have until now, but we hope to add some more results, and also some of the results might still be updated going forward. So the aim of the project is to really model time series of counts. Time series of counts appear in many applications. So I'm just listing a couple, for example, in medical sciences, meteorology, network modeling, but also in financial and applications or in economics. And towards the end of the talk, I'm going to show you an application in finance. When we talk about count data, I mean, many of you are experts, but I will just review it briefly anyways. So count data are non-negative and integer valued, and very often over dispersed, which means that the variance is typically much bigger than the mean. And recently, in some earlier work, we proposed the class of so-called integer valued trawl processes, which I will just abbreviate to IVT processes. And we found that these processes are rather flexible for modeling time series of counts, and also in a more recent work, I extended that class to a multivariate framework. So far, we have estimated these models based on a generalized method of moments which work to some extent, but we felt like there's certainly room for improvement when it comes to the estimation of these models. So in this new project, we really focus on improving on the estimation of these processes. And in particular, we wanted to look into likelihood-based approaches for estimating these integer value trawl processes. Also, you will see that the class of trawl processes is very broad. So from a statistical point of view, you might ask the question, how can we actually select models? So what's the best choice out of this huge class of trawl processes? So we want to look into model selection in a bit more detail as well. And also for applications, it's very important to be able to do some forecasting. So here in this project, I'm going to show you now also some results on probabilistic forecasting of these integer valued trawl processes. And as I mentioned before, we will look at an application to high-frequency financial data at the end of this talk. Okay. Okay. So there is a very broad literature on count data modeling and modeling time series of counts, and many of you are experts. So I apologize if your latest paper is not listed yet. We will obviously, make sure that we list all the most the relevant papers in our survey. Overall, I would say there are some maybe three predominant approaches in the literature when it comes to time series modeling of counts. So you find the so-called, for example, discrete autoregressive moving average processes, Dharma processes, which have been introduced by Jacobs and Lewis. And then more prominently, I would say there are the models based on so-called thinning operations, which goes back to the work by Stoitel and Van Haan. And these are essentially the models like the integer valued AR or AMA processes. And there is some recent work here on integer valued AR processes, and then also very prominently there are all these regression type models, typically based on generalized linear models. There are also state space approaches and Bayesian approaches. So there are many different approaches for modeling the time series of counts. Most of these approaches really work with classical discrete time series. Here in our project, we focus on a continuous time approach, where the model is formulated in continuous time, but obviously we assume that the observations will be in discrete time. So we will be using trawling for modeling counts. And this is a continuous time framework, basically using this kind of thinning approach. So let me give you a little picture. So this is really an explanation why we talk about trawl processes. If you think what trawling actually means, I'll give you a definition from Wikipedia, which says that trawling is a method of fishing that involves pulling a fishing net through the water behind one or more boats. The net that is used for trawling is called a trawl. And so technically, we will assume that we have essentially some points represented by our fish, which are in a two-dimensional space where we have the time dimension and an artificial spatial dimension. And we will catch the fish with our trawling net here, the fishing net. And we will just count how many fish are in the net. So in this particular case, I have 4 fish in the net. So that would mean the process at this point in time is equal to 4. Very soon, my 5th fish will enter the net. Then the process goes up and it will go up to level 5, say. And then we are actually very nice to our fish. So when they reach the boundary of the net, then we actually let them escape. So we don't catch them forever. And then when one fish leaves, then the level goes down, say, by 1 again. And so this is a process which takes integer values and can just, I mean, in the fish case, going up by or down by 1, but we will also allow for the fact that we have big or small fish, so that there can be changes which are different from 1. So this is, so you should keep this picture in mind. This is essentially the construction of our stochastic processes, and that's why they are called trawl processes, okay? Because we really have this picture of fishing in the sea in mind. Now I obviously have to make this a bit more rigorous. So if I want to model my fish formally, the most natural approach is to just use a Poisson random measure to model these points essentially in the sea, the fish in the sea. So let me define what we mean now by our stationary integer value trawl process. I denote it by x. It's essentially a Levy basis evaluated over a set AT. So let me make this precise. So L is an integer valued homogeneous Levy basis, and it's defined as an integral where I'm integrating with respect to a homogeneous Poisson random measure on Z, the interval 0, 1, and the real numbers. And I assume that this Poisson random measure has a specific compensator, which is given here by a measure eta, and then here I have the Lebesgue measure. And I assume that eta is a Levy measure, which satisfies an additional integrability condition. So this is essentially, so this Poisson random measure will generate the fish, the point in the sea. And then I have to say how I model the trawl, the fishing net. And this is here in the second point. So I start with a set A. A is also sometimes denoted as A0, the fishing net at time 0. And this is just a subset. I mean, I have some restrictions here, but you can just think of it as a subset in R2. And the only restriction we have is really that its Lebesgue measure has to be finite. Okay, so I assume that the Lebesgue measure of A is finite. And then if I want to compute this fishing net at different points t in time, then I'm just moving this net along. So this is what this means. AT is the set A, which is the fishing net at time 0, and then shifted by t. Okay, so the shape, everything stays the same, and I'm just moving it along in time. And typically, I have here an example. So this is the typical choice of the fishing net that we say at time 0, we are just considering points in the past. So S is the time index, it can go up to 0, and X is the spatial component. It's bounded by the time axis, so bounded by 0, and by the function, say D, which is what we call our trawl function. And now when we go up again here to this definition, you see the trawl process is defined as really, I mean, when you look at this functional form, this is an indicator function where we have the two variables, the spatial domain here and the time domain, and then we have our Levy basis. So this is a special case of a mixed moving average process, and as such, it inherits all the nice properties of mixed moving average processes. I'm just seeing the comments. Yeah. Okay, so these are our nice fish, not swimming in a polluted sea. Okay, let me show you a picture. So here, let's look at the first part of the picture. Here I have my black dots, which represent now all the fish of the same size, say. And so this is an example of what I call a Poisson exponential trawl, and I will make that precise in a second. This turquoise shape is now our fishing net, the trawl. And here, for example, we now need to count how many of the points are in the fishing net. So you see we have 1, 2, okay, 2 points. On the second panel, you see the realization of the process. So at that point in time, the process is at level 2. And then I have more points entering, more points dropping out. And you see this is essentially the path of this time series. And here, for example, let's just count again at the second point in time. And here I have 1, 2, 3, 4, 5. So I have 5 points in total. So at this point, say 18, we are at level 5. And so this is a very basic setup, but for many applications, this Poisson distribution is too restrictive because, as I said, often we have over dispersion, and then it's better to, for example, work with a negative binomial distribution. So here the story is very similar, but the difference now is that the points are of different size. Okay, so you can have big and small fish. So you can think of this as a marked point process, where the mark essentially represents the size of the jumps. And again, you now need to essentially add up these points, but you have to multiply by the size of the jump. So, for example, I have a jump of size 2 added to a jump of size 3 and so on, and I just add them up. And then you get here one particular sample path of such a negative binomial trawl process. So this is really just the picture you should keep in mind so that you have an understanding of how we construct these processes. Okay, so let me just give you some general properties of these integer value trawl processes. They inherit the properties of mixed moving average processes. And so as such, they are stationary, they are infinitely divisible, they are mixing, meaning they are weakly mixing, and ergodic, which is very nice from an estimation point of view. What is particularly nice is that they have a very nice structure for their cumulant function, which is the log characteristic function. So the log characteristic function of a trawl process here, of the process xt with parameter theta, actually just splits into 2 parts. It's the product of the Lebesgue measure of A. Remember, the A is the set, the fishing net at time 0. And then we have the cumulant function of a random variable L prime, say. And we call this random variable L prime, we call it the so-called Levy seed. And it's defined as the random variable which has this particular cumulant function. Okay, so what we see in this representation is that the distribution of the Levy's of the trawl process is uniquely specified by the distribution of the Levy seed, and also we find that for any infinitely divisible integer valued log pi, we can find a stationary integer valued trawl process which has pi as its marginal distribution. And this shows you that this class of processes is very flexible, and we also find that the autocorrelation function of these trawl processes is entirely determined by essentially the shape of the fishing net. Okay, so it's the Lebesgue measure of the set A at time 0, say, intersected with the fishing net A at time h, and then divided by the Lebesgue measure of A. And so this is a general class where you can essentially model the marginal distribution, which has to be in the infinitely divisible class independently from the autocorrelation structure. And so this is very nice for applications. Okay, so now I just want to show you the examples we considered in our empirical work. So as I said, so you could in principle have any compound Poisson type distribution with integer valued jumps. In the application, we focus on the Poisson case, so where we say, for example, L prime, this is this Levy seed, the random variable which characterizes the distribution of the Levy basis, follows a Poisson distribution. If you make that assumption, then the integer valued trawl process itself follows the Poisson distribution, and the parameter of the Poisson distribution has to be multiplied by the Lebesgue measure of A, say. And if you want to work with the negative binomial distribution, then you just assume that the Levy seed L prime follows the negative binomial distribution, and this will imply that the trawl process itself follows the negative binomial distribution. Okay, and now I want to show you how we typically model the trawl function. So the trawl, which is the fishing net. So typically we assume this is the same formula as the one I showed you before, that this is essentially a set in a two-dimensional space where we have the time axis and then an artificial spatial dimension, and the spatial dimension is modeled here via x, and s is the time variable, and we typically assume that the spatial component is bounded between the time axis and the function d. And then you can say, so how should we model d? So initially we just modeled this as an exponential function, but then in applications we found that this is often too restrictive. So we are now working typically with what we call superposition trawls. So here we assume that we have an exponential function, say exponential lambda s, but we associate now a distribution with the parameter lambda. Okay, and this distribution is described by this measure pi. And now, depending on what kind of choice I make for pi, I can get different shapes for this trawl function d. And I can now also compute my autocorrelation function again of this trawl process, and I can just express it in terms of these intervals of the d function. And this is something you can easily compute in practice. Okay, so this is actually quite nice. So all these computations are pretty straightforward, I would say. So let me show you now how we choose pi in practice, this measure here. So the easiest case would be to just say, well, choose pi to be the Dirac measure, and then I just get my exponential function back. And this is really the slide, the pictures I showed you before with these kind of turquoise shapes. These appeared when I chose an exponential function for the trawl function. In that setting, the autocorrelation function of the trawl process is just given by an exponential function itself. Okay, but this is rather short memory. This is often not good enough for applications. Then we used, for example, an inverse Gaussian trawl function. So this has now two parameters, and I just have the formula for the pi measure. But more interestingly, I get a specific formula for d and an autocorrelation function. So let's look at this. Rho is the autocorrelation function of the trawl. As you see now, I have this kind of square root of h appearing, and I have two parameters to play with. So this is an already much more flexible autocorrelation function, which typically actually describes the empirical data we study so far much better. Okay. The third choice I want to show you in final choice is if we pick pi to follow the gamma distribution. So if we assume that this mixing measure pi follows the gamma distribution with parameter 1 plus h and alpha, then I get a particular functional form for the trawl function. And here I show you the autocorrelation function. And the interesting bit with this autocorrelation function is that you can actually have truly long memory. So if this parameter h is between 0 and 1, say, then the autocorrelation function is not integrable anymore. So this gives us the possibility of having essentially a count data time series model which has long memory. And if you are outside that interval, say if h is bigger than 1, or you choose one of the other trawl functions I showed you, then we are in a short memory case. Okay. Okay, so let me now talk about estimation. So in the previous works, we really used the GMM method because the cumulant function is readily available, and this just worked very well. But we saw in the simulation studies that there's room for improvement. And this is actually very, very much in line also with what Claudia Krüppelberg presented earlier in the week when she compared her new approach to kind of the other methods for estimating Poisson-based count data time series. So here we are looking at a composite likelihood approach instead of the GMM approach. More specifically, we are looking at pairwise likelihoods. So I'm looking at essentially the pairs of observations, say xi plus h and xi. And I have to decide how many of these pairs we want to consider. So this is something we discuss in a bit more detail in the paper. I don't want to really go into the details here, but we are essentially constructing a pairwise likelihood for our trawl process, and we then maximize the log pairwise likelihood. And this is our maximum composite likelihood estimator. The main result here is that the pairwise probability mass function in the trawl case is readily available, and this is due to the fact that this integer value trawl process is so tractable. So let me show you this result, which is really nice. So this is the probability mass function of the trawl process evaluated at I plus h times delta and evaluated at I plus I times delta, say. In general, this joint probability mass function can be written as an infinite series where I multiply 3 probabilities together. And what we see now is that I have these. So L, remember, is the Levy basis, and here I have these various sets. So I evaluate the Levy basis over certain chunks of my fishing net, okay? And the Levy basis, by definition, is what we call independently scattered. So if you evaluate the Levy basis over disjoint sets, then the corresponding random variables are independent. And this property is really very, very useful for computations. And this is exactly what we use here. So you see, I have 3 different sets here. All these 3 sets which appear are disjoint, and that's what enables me to actually now split essentially the joint probability function into the product of these 3 probabilities. In practice, obviously, it's not so nice to have this infinite series here. It turns out that if I really focus just on count data, so on non-negative data, so if I assume the Levy basis is positive, then the sum is actually finite. So I can replace this infinite sum by the finite sum, and this is obviously much easier and faster to compute in practice. But also actually related to Claudia Kluppelberg's talk, I want to mention that there's also a simulation-based approach here for the trawl processes. So for example, here I just present this little formula. So we can also essentially use a simulation-based unbiased estimator of the pairwise probability mass function. It's still not of the full likelihood, but we could estimate it via simulation as well. And it has been shown in the literature that essentially MCMC-based estimation based on the simulation based estimation is quite useful as well. So this is also something we want to explore in a bit more detail, but for the rest of the talk, I will not focus on the simulation-based approach, but really on the pairwise likelihood approach. Okay, so first of all, we compared now in simulation studies the performance of the pairwise likelihood estimation versus the GMM approach, which we used before. And we are now looking at relative root median square errors of our estimations in the simulation studies. And the ratio is that way around, that if the ratio is smaller than 1, that means that our pairwise likelihood is better than the GMM, okay? And you see now we simulated various trawl processes. In the first column, we have the Poisson marginal distribution, and in the second column, NB is for negative binomial distribution. And then we have various trawl functions. The first row, we have the exponential trawl. In the second one, we have the inverse Gaussian trawl. And in the last one, we have the gamma trawl. And you see in almost all cases, the pairwise likelihood approach is significantly better than the GMM approach for parameter estimation. We find for some here in these 2 settings, negative binomial with inverse Gaussian and gamma trawl, we find that in these cases, the trawl parameter, the estimation quality of the trawl parameters is pretty much the same, whether we use pairwise likelihood or GMM approach. But still, for the parameters of the negative binomial, we are still doing better with the pairwise likelihood approach. Okay. So then one can also, there is an asymptotic theory associated with our pairwise likelihood approach. I'm not going to state the details, but we can use this asymptotic theory now to do some model selection for integer valued trawl processes. And there are the classical criteria like the AIC and the BIC criterion for model selection. And these have been adapted in the literature also for the use with composite likelihood methods. And this is really exactly what we do here as well. So we use a composite likelihood-based AIC and BIC criterion, and we estimate the corresponding asymptotic covariance matrices using a classical estimator and also parametric bootstrap type estimator. And we found that we can compute these model selection criteria quite well in practice, I want to really just show you now some simulation results where we just, checked how well do these methods actually work in practice, because I would like to stress that our methods, our models are generally not nested, okay? And typically these models are, these selection criteria are widely used in the case of nested models. So here we are looking at 3 model selection criteria. We have the composite likelihood itself, which is blue. We have the composite likelihood-based AIC criterion and the composite likelihood-based BIC criterion, which is the yellow one. And then in the top line, you see what's the true data generating process. So for example, in the first case, it's a Poisson exponential trawl process. That's the true process. And then we plot this selection rate. So in how many % of the cases did we pick essentially which model, right? Here, so I would say, for example, this is the Poisson exponential model. I simulate now several Monte Carlo runs. And then here I get around, say, in 40% of the cases, we picked the correct model. And then we have lower percentages for the other ones. So this is still not so great, right? But when we look at some other ones, so here, for example, I have the negative binomial exponential trawl. And here we pick the correct model with a much higher selection rate. So that looks already quite nice. And here the best example was the last one, where we picked the correct model in almost all cases. Okay, so these are some preliminary simulation results, but we still want to explore this in a bit more detail. But at least this gives us some indication of how we could formally select models within this integer value trawl class. Okay, and the final thing I want to show you now is how we can do probabilistic forecasting of integer valued trawl processes. So suppose now we have observations up to time t, and I want to predict the value at time t plus h for a positive h. And then, I mean, the traditional forecast would be an estimator of the type that I take the conditional expectation of xt plus h given ft, say. But such an estimator is not data coherent, in the sense that if we are looking at integer value time series, this conditional expectation is not generally integer valued, and this is obviously a problem. And also it has been widely recognized that this point forecasting is a bit limited. It would be much better to quantify the uncertainty, so to have a full probabilistic forecast. So we want to actually forecast the distribution of xt plus h given ft. And the problem is that our integer value trawl processes are in general non-Markovian. And that's the reason why the likelihood is also so difficult to compute for these general trawl processes. So then we thought, okay, let's do a trick. If this distribution of xt plus h given ft is not tractable, maybe we just use the same idea as in the pairwise likelihood estimation approach, that we predict xt plus h just based on the information of xt, and we ignore the past. So this is not identical, right? Because we're not dealing with the Markov process here, but we check now whether we can derive the distribution of xt plus h given xt. And it turns out that this works actually really well. Again, here we heavily use the fact that we have this very analytically tractable class of processes. So I can now compute the conditional probability mass function of xt plus h given xt. And it can be written as a finite sum of here this product of 2 probabilities. And I should say, after I have estimated the model, these 2 probabilities are known to me. Okay, so these are quantities which are fully specified. So I can compute them. I can, plug in the numbers in practice, and I can really compute now the full probabilistic forecast for, say, the time t plus h. And if you make specific choices, so for example, if you say you have xt is a Poisson trawl process, then we get a binomial predictive distribution. If we have a negative binomial Poisson process, we also have a specific formula. I don't think it's a name, it has a name, this distribution, but we will check. And but we have a specific formula for the for this predictive density as well. So this is quite nice. And then we implemented this now in practice. So for the last couple of minutes, I just want to show you now our application. So we looked at some high frequency financial data. In particular, we looked at the bid-ask spread of some equity prices, and specifically we looked at one particular stock here, Agilent Technologies, which is traded on the New York Stock Exchange. We just looked at one single day. This was quite a random pick, 4th of May 2020. The market is open from 9:30 to 4, but we got rid of the first hour just because we are dealing with a stationary model and there are lots of non-stationary effects going on when markets open. We cleaned the data using standard methods, and then we sampled the data equidistantly in 5-second intervals, and we had about 4,000 observations in total. The spread between the bid and the ask price, the minimum level was 1 cent. So we look at actually the time series of the spread -1 so that we get values between 0 and then any integer values. And then we run our model selection criterion, and we found that the negative binomial distribution was certainly the preferred one. And we found that the gamma trawl with a not long memory setup, okay, gamma trawl but not long memory was the preferred model choice. Let me show you the picture here. So in the first panel, you see the time series, and then in the first column, you see the blue bars. This is the empirical distribution of our spread data, and the red one is the fitted distribution. So in the first 3 rows, we fitted the Poisson distribution, and in the last 3 rows, we fitted the negative binomial distribution, which is a much better fit. And then here, in terms of trawl functions, we first fitted the exponential, then negative inverse Gaussian, and then gamma, and then again exponential, inverse Gaussian, gamma. And you see, frankly, you can hardly see a difference between the inverse Gaussian and the gamma fit. So these 2 models are pretty much identical. And we found that out of the models we tested, these were the preferred models. We then compared the forecast performance compared to essentially an integer valued AR1 process. And we compute the relative loss again compared to this competitor. And again, when the relative loss is smaller than 1, then our trawl process is doing better. And you see in almost all cases, we are doing better. So there are 4 losses we are considering: a mean absolute error and mean squared error for point forecasts, and mean logarithmic score, and the mean continuous rank probability score for the probabilistic forecast. And we also did we ran the Debord-Mariano test for testing whether forecast performance is identical between the competitor and our trawl. And in pretty much almost all cases, we rejected, and we found that the trawl was doing better in the forecasting. So let me conclude. So integer value trawl process, you should keep in mind as these kind of, we are fishing points in the sea. They give us a continuous time framework for modeling stationary serially correlated count data. From a modeling point of view, there are 2 components you have to specify. You have to specify the Levy basis, which generates the distribution of the jumps and the process itself. And then the trawl, which is essentially thinning the point pattern, and the trawl completely determines the autocorrelation function. We find that, these trawl processes are very tractable, and we find that the pairwise likelihood approach is preferred to the GMM estimation. We also used in our model selection criteria based on the pairwise likelihood approach, which worked quite well in our simulation. Also, we have now a method for probabilistic forecasting of these integer value trawls, essentially using this pairwise likelihood principle. And I showed you a first application where we forecasted equity spread data. And again, we could show that our trawl process is better at forecasting spreads up to 10 steps ahead compared to the integer valued AR1 process. Thank you very much.